Hello everyone, my name is Niko Trumbić, and today I will talk about a numerical model for bending fatigue lag prediction and gears with arbitrary tooth profile. So first I will give an introduction, I will present the numerical model, I will present how the calculation results intend to be compared with real world data, and do a short conclusion. So basically, gear root failures are the most common mode of gear failures, and they are usually influenced primarily by the geometry of the root fillet of a gear. In order to maximize the performance of modern gear drives, it is necessary to optimize the geometry of gears for the given application. In order to do that, one of the possible approaches is to adopt the asymmetric gear profile. That is a gear profile in which the pressure angle on both flanks, so the left flank and the right flank, is not the same. That way, it is possible to exploit a larger radius of curvature in the root of a gear in a tensile loaded zone where the crack initiates. Unfortunately, such geometry of a gear, its load capacity cannot be determined using the standard approaches outlined in ISO 6336 or similar international standards. Usually the way this is approached is using different numerical models, and analytical approaches are very rare and usually not experimentally validated. In this research, also the influence of asymmetric geometry will be taken into account using the finite element approach, but with a certain addition of a numerical model built to evaluate the data given by the finite element analysis model. So these are some of the standards which are usually used to analytically calculate the gears, which are unfortunately not applicable to gears with asymmetric tooth profile. They are essentially based on a cantilevered beam bending model with various factors added on top of it to take into account different parameters such as geometry, type of loading, and rim thickness, load distribution, and so on. So the determination of root capacity of asymmetric gears, as I said earlier, is usually done either completely numerically or in certain cases analytically, but such approaches are pretty rare. In this numerical model, the number of cycles to failure will be calculated in each gear or the root surface node, and the numerical model will consider the mean stress, residual stress, the fatigue strength reduction due to the notch-like effect of the tooth root fillet, the size, surface roughness, required reliability level, and the loading imposed on the part. Also, it is planned to use the model only in the high cycle fatigue loading regime, where we can eliminate or assume there are no plastic deformations. So first, we need to obtain the stress history data for the gear pair that we are about to analyze. The first thing that we do is we perform a finite element analysis on a 2D gear model. Why a 2D gear model? Essentially, this is done in order to save on computational time. Unfortunately, it is associated with certain assumptions which carry an uncertainty. One of those is that we now consider a physical 3D gear, that it has same probability of crack initiation in each of its sections. So we consider all of the sections the same and just simulate only a single one. Here you can see one such simulation. They are performed as quasi-static simulation with multiple numbers of steps. So basically with that, we are able to capture the neighboring tooth effect and as well the effect of a change in transverse contact ratio due to tooth bending under load. The simulations are performed at various load levels, and also they are performed for various gear geometries. By doing this, it is possible to assess the effect of changes in the pressure angle and the basic crack tooth fillet radius on the load capacity of a gear. Also, the results can additionally be modified to account for the dynamic effects or the phase load factor. Phase load factor being the unequal distribution of load along the length of the gear tooth, which cannot be taken into account using a 2D simulation, of course. So what is a neighboring tooth effect? A neighboring tooth effect is an effect which describes a slight compressive load happening in the tensile region of a tooth due to the subsequent tooth entering the contact. So if you look here at the tooth K being loaded, the tensile zone is in the root region of a gear just below the working flank. When this teeth exits the contact and the tooth after it enters, the zone which was tensile loaded on the tooth K is now here. the compressive zone of the tooth coming into contact after it is located here. And we can see that a certain point on the surface of this tooth root actually sees a slight amount of compressive loading as well. So this is this effect causes you can see it here. These are some of the simulation results which we have done in Abacus. And we can see that there is a certain amount of compressive stresses existing in the critical node in the tooth root. This, of course, has the effect of increasing the amplitude, the stress amplitude, but decreases the mean stress. This effect is also taken into the account with this calculation model. So once we get the stress history data, we need to also establish what are the allowable stress levels. So we start with data taken from literature for full reversed loading of an unnotched test specimen, because such data is much easier to obtain than obtaining data for the samples which are more similar to the final product. So testing a gear, for example, the data is much less common and also harder to obtain. So we start with an SN diagram, and we are first taking into account the size, the roughness, and the required reliability level. Once we've done that, we need to account for the fact that each tooth root surface node has a different and unique fatigue notch factor due to the different radius of curvature, the different values of mean stress in every node, and so on. Once we calculate this and take this into account, it is possible to establish a unique surface node SN diagram for every tooth root surface node. So each node has a different SN diagram associated with it. Once this is done, we can construct a modified Goodman diagram for every tooth root surface node. And then we can plot results of several FE analysis at different load levels on a curve and do a regression analysis to find basically a line. Here it is drawn as an example. It will be a line which explains at different load levels the behavior between the mean stress and the stress amplitude. We do this because we cannot say in a gear that the mean stress is constant, nor the stress amplitude is constant, nor the stress ratio is not constant, so we cannot take any of these assumptions. It is simply not the case. Once we have this, it is possible to calculate the factor of safety for every tooth root surface node, also taking into account the residual stresses. The residual stresses are introduced by the heat treatment, and they have a very large influence on the load capacity of the tooth root. Of course, it is quite challenging to establish the exact value of residual stresses. There are certain theoretical calculations that enable the theoretical the best way to give a theoretical prediction of the amount of residual stress. And then it is possible to establish the factor of safety for each tooth root surface node. This is very different than the approach given in the standard. The standard assumes where the critical node is located and calculates stress at that assumed location. But that location might not be the critical node. In fact, it is not. Usually, when we've ran a lot of calculations comparing the results for symmetric gears of the standard with this approach, and we see, as it is also reported in the literature, that the location of the critical node given in the standard is actually not exactly the same as the actual critical node in reality. So by doing this, we calculate the factor of safety in every node in the tooth root region, in the tensile loaded zone, of course, and we are able to calculate and determine what the critical node is without any a priori assumptions. Once this is known, it is possible to go back with the value of the stress, perform mean stress correction, and go back into the unique SN diagram of that surface node, the particular surface node, and determine the number of cycles to failure for that surface node. Once the number of cycles to failure is known, we can also do another set of analysis, which will give us the curve displaying the dependency of maximal principal stress in every tooth root node on imposed load. So we cannot say that by doubling the load that the maximum principal stress in critical node will double. So we make such a curve based on a large number of simulations. And then we get the curve which describes the effect, the dependency of maximum principal stress to the imposed load. When we have this curve, it is possible to say for the particular node, what is the maximum load that the gear can be subjected to achieve a required number of cycles to failure. Also, by employing this methodology, we can consider any contact nonlinearities, dependency of two-truth critical location on the load imposed, and we do not make any a priori assumptions about the location of the critical node. Once this is done, and the thing that remains is to make an evaluation of this model and see how it correlates with real-world test data. So at the moment, what we are doing currently is the test samples are being produced, which will be tested to compare the results which were calculated earlier with real-world loading data. So the gears will be made out of case hardening steel. They will be produced by single flank grinding to achieve basically any imaginable geometry of the tooth flank. In this particular case, they will be asymmetric gears. Also, some of the specimens will be used to measure the exact values of residual stresses using X-ray diffraction, so that we can compare the theoretical assumptions about the level of residual stresses with the real values that are present in the gears which are going to be tested. The gears themselves will be tested in an FCG type test rig, so they will be statically preloaded to a certain load level, and then they will be, of course, tested until failure. So the criteria is the complete failure of the tooth root, the breakage of the tooth root. The results of such a test for a number of test gears will be compared with theoretical predictions, basically to evaluate the suitability of this proposed model for determination of load capacity of gears with asymmetric tooth profile. Of course, one of the things is that due to the limitation of the test rig, it will not be possible to subject gears to a loading spectra. All the loading will be done at a certain load level so there will be no changes in speed nor the load level at which the test is being carried out. So basically, this is it.